Okay, so this is our video for lesson 10. We're going to talk about the idea of a function, how a function and that function's derivatives graphs are related. And then we're going to also look at the concept of differentiability, basically having a derivative, and then what would create a situation where a function may not have a derivative or the derivative may not be defined at certain points, and then how to prove differentiability. So 3 items. So here comes step 1. Let's talk about some functions. So first of all, we have a linear function f of x equals 3x. Okay. X's are individual values. The y values are 3 times each x value. And so if we were looking at a table of numbers that went with this graph, 1, 3, obviously 0, 0, 2, 6, 3, 9, and so on, right? Plotted along this graph, 3, and so that's the nature of this particular function. Sorry, I missed that eraser. 1, 2, 3. Okay. So if f of x is 3x, the derivative function, the derivative of 3x is just 3. Okay. When I graph the derivative, y equals 3, I get something that looks like this. At every x value, the y value is representing the derivative of f at that particular x. So the individual ordered pairs on this function, when I say x and y, and x is 1 and y is 3, and x is 2 and y is 3, and x is 3, y is 3, it's because at x, at any individual x, the derivative value is always 3. So here's a connection. There's a linear function. The linear function's derivative is a constant function. A line has one constant slope. This represents the function that is the slope of this line. If we go to something like an x squared, where I've got my points, where each y is related to x, such that we take the x and square it and get the y. For x squared, the derivative function would be 2x. If I were making a table for that, for y equals 2x, 0, 0, 1, 2, 2, 4, 3, 6, 0, 1, 2. I would have this. This is a picture of the slopes of x squared. If I look at x squared graphically, and we're going to talk about the slopes, x squared has a negative slope. That's right, has. I am not writing the word slope with any ability today. From negative infinity to 0. Okay, so this whole side of x squared has a negative slope. The derivative of x squared has negative y values from negative infinity to 0. This negative section, these negative y values, represent the negative slopes on x squared. It's kind of a hard set of pieces, a set of concepts to put together sometimes, how we're connecting the two different graphs. When I look at slope on this side, on the original, is y value on the derivative graph. Okay. How I look at the slope on the original function correlates with a y value on the derivative graph. So the x squared function has positive slopes. I don't know why that's not changing color. Positive slopes. Those are the positive y values. That match the positive slopes. Now, why this becomes important, why we care about this, is because we want to be able to look at a original function graph, and based on its slopes, match it to a graph of the derivative. So if I would look at an original function and I try to figure out, okay, where is the graph of that function's derivative, I should be looking at the slopes on the graph, negative slopes versus positive slopes versus zero slopes become negative y values, positive y values, zero y values. A common scenario is that you will be asked to, from a single function graph, asked to identify the graph of the derivative out of a set of choices, or potentially vice versa, from a derivative graph, be asked to match back to an original function. So let's do that sort of matching right now and talk through how 1, 2, 3, 4 match up with A, B, C, D. Okay. Probably the easiest one to start with is the one that looks like the one we just did. Graph number 2 is an x squared graph. Graph number 2 has negative slope and then positive slope. So the match would have to have a negative y value, negative y values, and then positive y values, and in between there have a y value of 0. So left to right, negative slope, zero slope, positive slope matches negative y, 0 y, positive y. So 2 and A are a match. The slopes on 2, negative slope and then positive slope, are shown on A by the negative y and then the positive y. This is where if we were together in class, I would stop and say, okay, see if you can find another one that might match. Okay. I'm going to talk you through the other three, but you absolutely need to practice this, and the textbook homework does have essentially some of these for you to practice. All right, so when I look at number 1 and I want to talk about the slopes, I see positive and then kind of 0 and then positive. So positive, I cannot write anything today. Positive, 0, positive slopes on this guy. So I need the same behavior for y's. Positive, 0, positive. And I'm hoping you realize that that's D. Positive y, 0y, positive y. On the left side, we're looking at slopes, and we're matching slope behavior to y value behavior. So 1 was D, 2 was A. Let's talk about 3. Positive slopes, lots of positive slopes, but undefined spaces. So positive slopes and then nothing, and then a bunch of positive slopes and then a gap, and then a bunch of positive slopes. So all positive y's, but gaps. That's going to be B. All positive. All positive slope, all positive y. On number 4, really big slope, almost undefined. Positive, but getting smaller. So positive slope, big to small. So positive y's from really infinitely big y's to really small y's, 4 matches with C. This is where you would definitely want to go to the textbook work and practice doing this kind of matching. We'll also have a review later where we will do another practice with this, looking at some graphs and some derivatives and matching them together.